Hello class, welcome to SciChem. Here we are another session for lecture 7 of chemical kinetics. Before watching lecture 7, make sure that you have watched previous lecture, that is lecture 1 to 6. So here we are. In the previous class we have already discussed about zeroth order, first order and second order reaction, and here we are going to discuss about nth order kinetics. So here nth order kinetics may be defined as the rate of reaction depends upon nth power of concentration are called nth order kinetics. So let us consider reaction A gives rise to product and rate is equal to K into A power n. So in case of rate I can write here minus dA by dt is equal to K into A power n. So by solving right here minus dA by A power n equal to integrating both side table, you can get minus dA by A power n integration A naught to d A dt to it will be equal to A power minus n plus 1 divided by n minus 2t and it will be equal to t. By solving this I can get 1 by n minus 1 a power minus n plus 1 is come to below and it will be a power n minus 1, and by solving the limit I can put here 1 by a t power n minus 1 minus 1 by n outer power n minus, and it will be equal to 80. So this is rate constant for and derivation of rate constant for nth order, and we have to calculate T half for nth order reaction. T half for nth order. T half for nth order reaction at T is equal to T half, we have AT is equal to A naught by 2, and we have nth order kinetics KT is equal to 1 by n minus 1 into 1 by AT power n minus 1 minus 1 by A naught power n. By solving I can get K into T half is equal to 1 by n minus 1 1 by A naught power A naught by 2. In case of AT I have to put A naught by 2 power n minus 1 by naught power n By solving this, I get t half is equal to 1 by k into 2 to the power n minus 1 divided by n minus 1 into a naught to the power. So this is t half for nth order kinetics. You can easily a naught by 2 means a naught to the power n minus 1 divided by 2 to the power n minus 1. I have taken 2 to the power n minus 1 ever. So 2 to the power n minus 1 minus 1, and below there is a naught to the power n minus 1. So this is t half for nth order reaction, and this is all about nth order kinetics. Let's come to next part, effect of temperature. We have already discussed effect of temperature. On increasing temperature, rate of reaction increases, and normally it is found that on increasing temperature by 10 degrees Celsius, rate of reaction increases by 2 to 3 times. Here another important concept is temperature coefficient alpha. Temperature coefficient is denoted by alpha, and it is defined as the ratio of a rate of reaction at two different temperature differ by 10 degrees Celsius. Temperature coefficient may be defined as the ratio of rate of reaction. Ratio of rate of reaction differed by 10 degrees Celsius. And that will be equal to here R, that is R T plus 10 divided by RT equal to R. Normally the temperature range is 25 to 35 degree Celsius. That is RT plus 1, or I can simply write here R 35 degrees Celsius by R 25 degrees Celsius equal to alpha. This is alpha is the temperature coefficient. So temperature coefficient may be defined as the ratio of rate of reaction at two different temperature, at 35 degrees Celsius and 25 degrees Celsius, and which in which the rates are differ by 10 degree Celsius. And we are gonna solve a problem, that is, question is, if rate of reaction at 25 degrees Celsius is R and temperature coefficient is alpha. So writing R 25 degrees Celsius is given, tell R. Just take it small. R 25 degrees Celsius is equal to small r, and given temperature coefficient is alpha. Then calculate rate of reaction at 35 degrees Celsius and 45 degrees Celsius. By using the above formulae, I can write R 35 degrees Celsius divided by R 25 degrees Celsius is equal to alpha, and I know R 25 degrees Celsius is equal to R. So rate of reaction at 35 degrees Celsius equal to alpha into R, or alpha into R 25 degrees Celsius, and R 25 degrees Celsius have value R. And similarly, here is another question, calculate rate of reaction at 45 degrees Celsius. So R 35 degrees Celsius, I have calculated alpha into R. So R 45 degrees Celsius divided by R 35 degrees Celsius is equal to alpha. This same 10 degrees Celsius. Difference is above and below, the difference is 10 degrees Celsius. So value of R 35 degrees Celsius is alpha R. So rate of reaction at 45 degrees Celsius will be alpha into R into alpha. That will be equal to R 45 degrees Celsius equal to alpha square R. So the simple problem. Next, we have to start effective collision theory. In order to carry out a simple reaction, the molecule must collide. In order to collide the molecules, the collision should be effective. And this is effective collision theory. Let us consider A2 plus B2 gives rise to 2AB. So A2 means this is A molecule plus this is B molecule, and they undergo collision to give the. So come to point 1, number of binary collision. Number of binary collision means two molecules undergo collision. Observed per second per unit volume at room temperature is 10 to the power 27 times. That means the number of collision, the molecules which undergo collide, have been observed that per second per unit volume the number of binary collision is observed, that is 10 to the power 27. That means if two molecules undergo collision in a beaker, there are more number of molecules and they undergo collision, that will be a binary collision, and this binary collision is 10 to the power 27 times. If all these collisions are effective, then reaction should be completed within a fraction of second. If the 10 to the power 27 times collisions are effective, then reaction should be completed within a fraction of second. But normally reaction requires a finite time to complete because most of the collisions are ineffective or non-effective in nature. If we consider a beaker and there are various molecules are present and these molecules undergo collision with each other, and this collision number is 10 to the power 27 per second per unit volume. If all the 10 to the power 27 collisions are effective in nature, then the reaction should be completed within a fraction of second. But normally it has been found that the reaction requires a finite time to complete because all the collisions, binary collisions, are not effective or non-effective or ineffective. So come to point 2. For a collision to be effective, it should overcome two types of barrier, that is energy barrier and another is orientation barrier. Then come to point 1. What is energy barrier? A molecule must collide. A molecule which undergo collision with each other should have sufficient kinetic energy. So here another term is developed, that is energy barrier means threshold energy. Threshold energy means the minimum energy required by the reactant molecules to convert into product is known as threshold energy. That is, the reactant molecule should possess the minimum energy in order to convert into product, that is called threshold energy, which is denoted by ET, and it is fixed for any given reaction independent of temperature, and it will be different for different reaction. Remember, threshold energy is fixed for any reaction. It is independent of temperature and it will be different for different types of reaction. Threshold energy. So if energy of reactant is less than threshold energy, then the collision is non-effective. Then the collision is non-effective in nature. But if energy of reactant is greater than threshold energy, then the collision is effective, but depends on orientation factor. If the collision to be effective, there should be sufficient amount of energy, that is the reactant molecule possesses sufficient of amount of energy, and that should be greater than threshold energy. And what is threshold energy? Threshold energy is the minimum amount of energy should be possessed by the reactant molecule in order to convert into product. So if ER less than ET, or if energy of reactant is less than threshold energy, that is called non-effective, the non-effective collision. If energy of reactant is greater than 80, that is called effective collision, but it would depend upon orientation barrier, because in order to the binary collision to be effective, it should overcome two types of barrier, that is energy barrier and another is orientation barrier. We have discussed about energy barrier, then come to next part, that is orientation barrier. In orientation barrier, molecules should be properly oriented for maximum impact or to form product. So let us consider a reaction here. A plus Bx gives rise to B plus Ax. A is a molecule, Bx is a molecule, gives rise to B plus Ax. So this type of collision, A B in Bx, this is ineffective collision, but Bx into A, this is effective collision. So in order to form product, the molecule must collide with proper orientation. So we have considered two types of molecule, that is A2 and B2. Let us consider for proper orientation as A, this molecule undergo collision, B. During this collision, this is reactant molecule, they have kinetic energy maximum, potential energy minimum. For reactant molecule, since they undergo collision, they have kinetic energy maximum and potential energy is minimum. When they collide, the bond between AA molecule breaks, BB molecule breaks. The bond between AA breaks and BB breaks, and new bond is formed between AB. What happens during collision? During collision, the bond between A and A breaks, B and B breaks, and new bond is formed between AB and AB. So simultaneously the bond is formed and the bond breaks. Simultaneously takes place. Simultaneously both the phenomena, bond formation and bond breaking, takes place. So this type of state is called transition state. Product is still not formed. During the collision, the bond between A and A breaks, B and B breaks, but the new bond is formed between AB. So this type of state is called transition state, and this transition state is also called activated complex. And they are highly unstable. Because they have kinetic energy is very low, but potential energy is very high. If any compound which have higher potential energy, they are unstable in nature, and this activated complex will gives rise to product B. So this is the whole reaction, and the product formed which have kinetic energy is very high and potential energy is very low. This is the progress of reaction, and this is the binary collision. All the binary collisions are ineffective. The collision to be effective, the molecule should collide with proper energy and proper orientation, and during this collision a transition state is formed. This transition state is called activated complex. It is highly unstable, and the transition state is, since the transition state is highly unstable, it is converted into product, and the product have kinetic energy is very low and potential energy, sorry, kinetic energy are very high and potential energy is very low. This is the all about the progress of reaction. If we study the progress of reaction, we found that reactant, first there are reactants. In reactants, bond dissociation dominating phenomena. That means in reactant the bond breaks. During the formation of transition, reactant molecules undergo dissociation of bond in case of A and in case of B. So bond dissociation dominating phenomena, and during this process energy is absorbed. In case of reactant, bond dissociation dominates, so energy is absorbed and transition state is formed. Take it, transition state is formed, and this transition state undergoes bond formation, dominates, and product is formed, and here energy is released. During bond dissociation energy is absorbed, and during bond formation energy is released, and this is all about the progress of reaction. Then come to another part, that is concept of activation energy. If you remember, this curve is Maxwell distribution curve. Here I can explain why with increasing temperature the rate of reaction increases. So let us consider a graph, Maxwell graph. If we study the graph in x-axis, we have to study fraction of molecule, or in y-axis, in x-axis it is energy, and the topmost energy is ER, that means energy of reactant, and this energy is called threshold energy. So what is threshold energy? Threshold energy is the minimum energy must be possessed by reactant molecule to converted into product. So minimum energy, and ER is the reactant, ER is the reactant molecule having, so fraction of molecule means these are the molecules which are present in the bell shaped area below the bell shaped curve. It is area below the bell shaped curve. So this is ER and this is ET, and this fraction of molecule, possesses energy more than threshold energy. This fraction of molecule, this fraction of molecule possesses energy more than threshold energy. So this fraction of molecule can be converted into product. If I have to increase then what happens here? Curve follows this type. What happens here? Threshold energy does not change. I have already studied. because threshold energy, what is threshold energy? It is fixed for any given reaction independent of temperature, and it will be different for different reactions. Since the threshold energy is independent of temperature, that means threshold energy does not change, but there is increase in number of fraction. There is increase in fraction of molecule, increase in fraction of molecule participating reaction. Increase fraction of molecule. So with increase in temperature, the rate of reaction also increases. So this is all about Maxwell's Boltzmann distribution curve. So in order to give the extra energy, you have to supply this much, and this energy is called activation energy. In order to take the molecules from here to here, we have to supply this extra energy, that is activation energy. So what is extra activation energy? The extra energy must be supplied to reactant molecules above their average energy level to make them participate in the reaction is known as activation energy. So again I am drawing the curve. This is ER, is if the reactant to be converted into product, means ER be less than, and this fraction of molecule should possess energy greater than 80. So this much amount of energy should be supplied to the reactant molecule in order to participate in the reaction. So in other words, I can say activation energy is equal to threshold energy minus energy of reactant, or threshold energy is equal to activation energy plus energy of reactant. So what is ER, ET? ER means the reactant molecule possessing energy. ET means the minimum amount of energy must be possessed by the reactant molecule in order to convert into product. EA means the extra energy must be supplied to the reactant molecule in order to pass the energy barriers, that is threshold energy. So this is all about energy of reactant, threshold energy and activation energy. If we come to graphs related to activation energy, this is potential energy and this is reaction coordinate. Reaction coordinate means progress of reaction. We are studying the progress of reaction by using potential energy. Similarly, potential energy, reaction coordinate is also called progress of reaction. So let's consider here reactant molecules are present and they have energy ER is energy. If I put a ball here and this molecule will undergo reaction to form product, here it is the energy of product, it is ER, it is energy. This molecule will convert it into product only when they have energy sufficiently equal to threshold. Since reactant molecules have insufficient energy, we have to give this much amount of activation energy. If we supply this much amount of energy, this molecule can be participate into product, reaction, and can be converted into product. Here I can say delta H is equal to EP minus E, and this is ER and this is EP, and ER have energy more than EP. So I can say that delta H greater than 0 and it is endothermic. In similarly, here the molecule is reactant molecule, here is the product molecule EP and the top E. In order to this ball participate in a reaction, the molecule should possess this much amount. The extra energy should be added. This amount of extra energy is called activation energy. So here I can say delta H is equal to EP minus ER, but energy of product is very less than energy of reactant. Sorry, I made a mistake. Graph is wrong. Sorry. Here ER, here EP. Here EP have energy less than ER. EP have energy less than ER. That means delta H is less than 0. EP have energy less than ER, so delta H less than 0. So this is not endothermic, it is exothermic. Here ET, in order to convert it into product, that means this much amount of energy is required, that is activation energy. So here EP is more than ER, so delta H is equal to EP minus ER, and here delta H is equal to 0. This is endothermic. This is endothermic reaction. So this is the graphs related to activation energy. Then come to next part, Arrhenius equation. So what happens here, the fraction of molecules which are crossing energy barrier, here the fraction of molecule, this fraction of molecule, the fraction of molecules which crossing energy barrier, that is threshold energy barrier, the fraction, it have been found that the fraction of molecules which are crossing energy barrier is equal to e to the power minus EA by RT. Experimentally it is found. And rate of reaction directly proportional to the fraction of molecule crossing energy barrier is also true. Fraction of molecule which crosses, this fraction of molecule which cross energy barrier, fraction of molecule which cross energy barrier is equal to OM, fraction of molecule crossing energy barrier is equal to e to the power minus A by RT. And this fraction of molecule is directly proportional to rate of reaction. More is the fraction of molecule, more is the rate of reaction. So here I can write rate of reaction directly proportional to fraction of molecule crossing energy barrier, that will be equal to e to the power minus by RT. And we have rate is equal to K into concentration per order. Since for a reaction, reactant have constant concentration, In order to reaction to be happen, the reactant molecules should have constant concentration. So here concentration is constant. If the concentration is constant, then rate is equal to K. So in terms of rate, in case of rate, I can put K. So rate constant directly proportional to e to the power minus. By removing proportionality constant, I can put here K is equal to A into minus A by RT. This is so called Arrhenius equation, or variation of rate constant with temperature. These are the important points you have to remember, where A is a constant known as Arrhenius factor, collision factor, frequency factor, or pre-exponential factor. This equation takes account of that molecules which have proper orientation. A has same unit as K. Why A has same unit as K? It have no unit. So A has same unit as K. This equation is not applicable for, sorry, not K, radioactivity. This equation is not applicable to radioactivity reaction. So this is all about nth order Arrhenius equation and effective collision theory. This is the important concept. So what is effective collision theory? If you consider there are several molecules in a beaker, and the molecules undergo collision with each other, this collision is called binary collision, and it is observed that the number of collision per second per unit volume is 10 to the power 27 times. If the 10 to the power 27 times collision is effective in nature, then the reaction should be completed within a fraction of second, but normally the reaction takes place a finite time. As the reaction takes place a finite time, that means all the collisions are not effective. Some of them are effective. So what are effective collision? If the collision to be effective, the molecule should possesses two types of barrier or cross two types of barrier, that is energy barrier and another is orientation barrier. We have already discussed. Thanks for watching. Thanking you.